So our next speaker is a Professor Yannis Aloimonos. Sorry about my pronunciation, maybe wrong. He's from the Department of Computer Science, University of Maryland, and then he's leading the Computer Vision Laboratory. So I'll leave the stage to you.
Yeah, thank you. Thank you very much. This talk is going to combine ideas and concepts from mechanical engineering, electrical engineering, optics, and computer science. So there's a little bit for each one of you. We are very happy to be here in your beautiful workshop. I have always been interested in robotics for a very simple reason. There is no other way to test theories of intelligence. Because intelligence is an amalgam of a number of capabilities and competencies, such as perception, vision, sound, tactile processing, proprioception, planning, reasoning, natural language. All of this, they come together in a robot that is performing tasks and communicates with humans. There is no other problem where all of this come together. This is why we have been employing robots in our work. So today, we are always strive for new ways of expressing ourselves. And for today's talk, we would like to present to you a Socratic dialogue that I will do with my student and friend, Botao. So sit back, relax, and enjoy the little presentation. Welcome, Botao. You said in your letter that you wanted to study perception for robotics.
That's what people said. It's the future of robotics.
Next year is 2025, and it is 60 years since the founding of the Computer Vision Laboratory in Maryland by this man, Asher Rosenfeld, who was a giant in the field. He developed the first journal of the field, the first conference, and he defined the field of computer vision. So people have been looking at images for about 60 years, trying to develop algorithms for understanding the world. But there is a new camera that came out. It's called a DVS, or event camera. These are neuromorphic sensors. And you can see here in this video, on the left, you have an RGB camera, and on the right, you have this DVS camera. And what I'm doing is I'm throwing an arrow with a bow in the room. Now, if you look at the DSLR camera, if you have good vision, you may find the arrow in 2 or 3 positions. But if you look in the DVS camera, you clearly see the arrow moving in the scene. So this new camera is very good for fast motion, but not only. Let's see some examples. So here, the camera is looking at me. And if there is no movement, you don't see anything. If there is a movement, then what the hardware does, it goes to every pixel, and if it records a change in the intensity of the pixel, then it goes there and puts a point. That point is called an event. And you can give them different colors depending on whether the change is positive or negative. So basically, these images are a bunch of points that are moving disappear and appear. So here you can see if you have a wheel turning and there's a point, the standard camera, you are going to get those images. In the DVS output, however, you get the events, and if you connect them through time, then you are getting the new input as you see. As you see in the right, if you have fast motion, you get blurring with a standard camera, while with a DVS, you're not getting any blurring. And here you can see cases of imaging with challenging illumination on the left, high dynamic motion segmentation in the middle, and on the right, you can see high-speed videography where you have a bullet that is hitting that object and it's breaking into 1,000 little pieces that you can track. So these event cameras are amazing, but they have a problem. They have a problem, despite the fact that biological systems and humans, they have those images as well. They are on top of the images that we see. We have cells that detect these changes. So here's the problem with these cameras, Botao. The output that they will give depends on the movement that they have. So if the movement of the camera is along a line, then the camera will lose the events along this line, as you can see very convincingly in this presentation.
Since humans and animals, they also like using event-based vision, how do they like handle this problem?
The humans, they are using an amazing active system that is based on microsaccades. Let me show you.
Actively perceive the world through eye movements. Regular eye movement alternates between saccades and visual fixations. Even during visual fixations, our eyes are never completely still, as there exist microsaccades. Microsaccades are a kind of fixational eye movement. It continuously stimulates the visual neuron by constantly jittering the eyeball. Microsaccades are believed to enhance the vision of fine spatial detail and prevent the retina image from fading. The following demonstration interactively illustrates the effect of microsaccades. Viewers may watch this movie in full screen mode, stay close to the screen, and fix the gaze on the red spot. You can pause the video here to observe. After
Sorry. Let's pause it for 5 seconds.
So fading is going to happen.
observe.
So basically, what is
After
happening
seconds
with
of fixation,
biological
you may
systems,
observe the image fade, like this. This is due to the suppression of microsaccades. For comparison, viewers can then fix the gaze on the moving red spot. You may observe the elimination of perceptual fading because of microsaccades.
so what biological systems do with the microsaccades, they are jiggling the eyeball. The eyeball is continuously jiggled, and that way they don't miss any events. So a good problem for you, Botao, would be how to work with those cameras so that you don't lose those events that are happening at various places depending on the input.
Does that mean we need to introduce microsaccade into the robotics vision?
Obviously, to jiggle the camera is not a smart way. It's not a good engineering solution. You will have to think outside the box, and you will have to be creative in trying to address this problem.
I see. So the question is, how can we utilize advantage of event cameras while also keep the texture stable? Here's the next part. All right, I figured out a way of solving this problem.
You figured out how to solve it?
Yeah.
I'm all ears.
So here's the basic idea. Instead of just shaking the camera, just like Microsaccade does, which is a bad engineering solution from my perspective, I put a rotating wedge prism in front of the lens. It can rotate the bundle of incoming light and introduce continuous microsaccade at every point of time. I have a video. So we proposed a hardware-software co-design to introduce microsaccade.
So you call this camera AMI-EV?
Yeah, artificial microsaccade enhanced event camera. So we put a rotating wedge prism in front of the aperture of the event camera to generate events.
So you are putting a prism in front of the lens
Yes.
and you are rotating it.
Yeah, and since the rotation is observable, the motion can be compensated so that we can get a very sharp image output. This can be used as a plugin and use solution with existing event-based algorithms.
So instead of jiggling the camera, you are jiggling the bundle of the light rays that is going inside the camera
Yeah,
by doing the rotation of the prism.
yeah, here's the.
So it is as if you introduce a microsaccade at every instant in time
Yes,
without moving the camera.
yeah.
This is a brilliant idea, Botao.
This is a more detailed mechanism.
This movie introduces our mechanism for generating and compensating artificial microsaccades. To generate events on all edges, we utilize the working principle of the wedge prism deflector. When the prism rotates, it actively adjusts the direction of the incoming light. Here we illustrate our hardware design. It features an actuator driving a rotating wedge prism and recording its circular path. This rotation induces continuous changing motion in the camera, capturing all scene boundary information. After that, because the introduced motion is observable by the actuator encoder, we can compensate for events triggered by the same incoming light ray direction to the same pixel. Finally, we can get sharp and stable edges. The compensation algorithm makes our system a plug-in and use solution with existing event-based perception algorithms.
This is amazing. This is really very impressive. What you really have to do now is to use this new camera in order to solve specific problems in vision.
So what kind of problems?
Well, I would recommend you pick problems at a low level, like the output of the camera itself, problems at the middle level, like tracking features in the images and the videos, and problems at the high level, like recognizing things or recognizing the pose of a human, for example. These are problems where the conventional DVS cameras are having difficulties.
I see, so let me look into it. So here's, I studied these problems, and here are the results. So in brief, in all tasks, our system works much better. Our system can
Can be
fundamentally
unstable due to perceptual fading when static or moving in certain directions. This fading often generates low-density noise events lacking useful structural information. Our system mitigates this and ensures a more stable event stream with reduced low-density noise. For accumulated event images, the output of our system is proven to be more informative and stable.
It is such a striking
In
difference
terms of
between the two.
reconstructed intensity images, our system is proven to have higher image quality and maintains consistent performance across varying movement directions and speeds.
So our systems improves the quality of the output events with different event representations.
With a standard event,
And for specific tasks, for low-level vision tasks, we choose the feature tracking and motion segmentation. Here's the environment. It's conducted in 4 scenarios. First is simple, second is complex, third one is have a very high dynamic range, and the fourth one is motion segmentation. So for the first one, both our system and the RGB camera can perform well. However, the standard event camera, due to its perceptual fading, or it cannot stay maintain stable texture, the color detection.
The standard event camera is losing many of the features.
Yes.
But your new AMI EVV doesn't lose any.
Yes. So for each red point in the image, that's not a feature point that be detected at this time step. It's a point that be detected and tracked over 100 milliseconds. For the unstructured environment, our system is not as good as the RGB camera, but still outperforms the standard event camera. And also for the high dynamic range, like challenging illumination environments, the RGB camera and the event camera just fails, but our system can maintain very stable performance. For the motion segmentation, it indicates that our camera also preserves the high time resolution feature of event camera. It doesn't lose anything, but it gives you a very stable texture as a bonus.
So the gray camera is losing the moving object.
Yeah.
Because it's moving so fast.
Yeah, too fast.
So you have nothing inside. It's like my arrow.
Yeah. So for high-level vision tasks, we choose the human detection and the pose estimation. In a scenario where there are both like static objects and moving parts, the standard event camera can have perceptual fading, but our camera can easily achieve thousands of FPS reconstruction and do better pose estimation.
And you can always find the pose.
Yes.
Because when you have a video now of a human doing something,
yeah,
you need the sequence of poses so that you can recognize the action.
Yeah.
But if you lose the skeleton, then you cannot do this problem.
Yeah.
So the AMI V is very consistent with the skeleton.
Yeah.
Congratulations, Botao. Look, a significant event has happened recently.
Yeah.
These DVS cameras are now going to start coming into the Samsung cell phones by the billions. And the number of applications is sort of amazing. Now, clearly, your camera is much better than all the cameras that are in the market. But you have something rotating.
Yes.
So is it possible, maybe with help from people like the previous speaker, to replace the rotating prism with some material that doesn't move, but affected by some voltage, for example, it can have the same effect like the rotating prism?
Yeah, so I think there are 2 typical ways. The first one is through mechanical engineering, like we build a small actuator, just like the optical image stabilization modules in everyone's phone, that it's a very small module in front of the camera sensor that can shake, like produce a certain movement to compensate the ego motion, so it's smaller and more lightweight, but currently it's it cannot shake the lens at a very high frequency, which can cause many problems, and it can be hard to achieve circular motion. Also, there's currently no compensation modules for these shaking movements. I think the frequency and the circular motion is not a big deal because we can choose to generate certain types of motion. Like if our camera moves horizontally, we generate a vertical motion and vice versa. But compensation can be a problem. If we cannot compensate the motion, we cannot get the sharp edges. And from the material perspective, maybe we can have electric optical materials that we change the applied voltage on the material to change its deflection or reflection properties. I think there are 3 possible materials, but I'm not an expert in this area, so I don't want to provide too much.
Ladies and gentlemen, here is the camera that Botao has made, and you are welcome to come and see it at the end of this. And we would like to thank you very much for your attention.
More information, you can scan the QR code to check our website. So any questions?
There is a paper, this paper that you see up here is going to appear in Science Robotics next week.
Yeah.
And we would like to especially thank Cornelia Vermeulen for her contributions to this. And as you see, this has been a collaboration between our lab and a lab in China at Zhenjiang University.
Thank you.
Okay.
So I think it depends on where you want to apply this. You use this camera. For this generation, we made it around 100 grams, but it's still too much for a phone. But maybe if there are many other applications, like if we want to detect the motion, it can be used as a high-speed camera. It compared to the other high-speed cameras that weighted like a couple of kilograms, it's much more lightweighted. But compared, yeah, 100 grams. Also for frequency, also for the frame rate, as we tested in this task, we can achieve like over 3,000 FPS, still maintain a good performance. For this one, it rotates at like 12 hertz. Yeah, like 12 circles per second. Yes. I think it's a list of pixels that has brightness change. Yeah, it's like a point cloud instead of an image. Yes. Yeah, you mean simulator? Okay, can I rephrase your question? Like you want to ask can we just achieve the same effect without moving the pixels, like rotating the lens? Yeah. Post-processing may be hard because the information cannot be generated by the camera. If there's no information, there's no post-processing can be done, right? The event camera only records the moving things. So if you don't move it, oh yeah. But let me extend your question for if we can change the phase of or the intensity of the incoming light without moving the pixels, we don't even need to compensate it. Okay. Oh. Okay, thank you. Yes. What do you mean range limitations? Do you mean the distance we can capture? I think it fully depends on the lens, aperture, and just like the traditional RGB camera.
Inside the room to have.
Sorry.
For use inside the room to deep space.
Yes.
Actually, they have these cameras now, a new application, because you can see the satellites from the Earth using this camera. And the government started using them for various operations. Okay.
Thank you.